lecture series on complex analysis for undergraduate students. Today's topic is contour integration. We have talked about the integral of complex functions defined on real domain, and there we had find it out that the complex function we can break into two parts. Both parts could be treated as real functions on the real domain. Then we have come up with the complex function on the complex domain, that is the function argument is also complex variable. There we had seen that we would be talking about the integral between the 2 points as the 2 points on the plane, and we can reach to the from one point to the other point in 1,000 many manners. So, we thought is that is it could be that is it is depending upon how we are moving along which path to reach to the other point, so that the function could be defined on that path and then we could do. So, we have defined certain paths, we call them arcs, curves, simple curves and so on. So, what is this contour? Let us define the contour. Contour is a piecewise smooth arc, that means an arc consisting of finite numbers of smooth arcs joined end to end. What it says is that if z is equal to zt defined from on the interval a to b is a contour, if zt is continuous and z dash t is piecewise continuous. If you do remember, a smooth arc we meant is that the arc is differentiable and its derivative is not 0 on the whole interval. So, here we say is that piecewise smooth means it could be zt is continuous and z dash t is also piecewise continuous, and its derivative that z dash t is not 0 at all at any point on the interval a to b. Say for example, if I do take this function zt, which is defined as t plus it between the range 0 to 1 and t plus I in the range 1 to 2. So, let us see that is what this would look like. This is actually t plus it from the for the range 0 to 1. This is actually the straight line from 0 to 1 plus I, and then we do have the straight line from 1 plus I to 2 plus I. So, we do have here two arcs which are joined from one end, that is where this arc, first arc is ending, the other arc is starting from here. So, they are joined with. Let us see, that is we say is that it should be a smooth curve. That says is that I should have the differentiable arc. Of course, we see from here that these functions are continuous and differentiable. If I take the derivative of this zt by using this complex differentiation, I would get here 1 plus I, and here I would get 1. So, at 1 if we see this function is continuous, because at 1 the limit from the left would be 1 plus I and from the right would also be 1 plus I. But if I do take the derivative at 1, it would be here 1 plus I and here it would be 1. So, it is discontinuous at this point, the derivative. So, it may be that is at most piecewise continuous, while as at all other points the derivative will also be continuous. So, this is one example of a smooth arc. As we have done this in the arcs and curves, that is simple arcs and simple curve. Similarly, we can define here also simple closed contour. That is, if the initial point and the end point, that is a and b, they are same, then the contour is called the closed contour. Again, we do have the same kind of examples as any closed arc oriented one. So, say for example, this is circle oriented towards anti-clockwise, this is one contour. If the orientation is clockwise, it would be another contour. Or this rectangle, if you say is that this point we are starting, then we are oriented in this manner, that is we are starting from this point, moving over here, then in this direction, then in this direction and then in this direction. Now, this is a contour because all the arcs, they have been joined end to end, they are all straight lines and they have been joined end to end, and this is the same, the orientation is in this manner. Now, the same arc we could say is that it would be contour if I take the orientation other way around, that is if I take the orientation from this way around, then also it is a contour, but that would be sharp-edge contour, that what we are having. Similarly, if I do have this triangular kind of shape, again if I start from here, we do have that orientation is from this side to here, then from here to here and then here to here. So, again we are joining three straight lines in this orientation. Now if I change the orientation, that is, let us say, that is if I am starting from this side and this way, or if we take any other point and then the orientation is being changed, all those would be different contours. From here one thing is clear, because we are talking about contours. Contours means is its z dash t is piecewise continuous and it is not 0 at any point. That says is actually that z dash t is integrable in the whole range t is equal to a to b. What it says is that length of contour can also be find it out. Since contour is nothing but the sum of, or that is a joint of simple arcs or simple curves which are differentiable. So we do say is that length of a contour, if it is single piece, that is as in this first example, it would be simply integral of z dash t along this line, or from the whole point A to B, or if it is joining of many smooth arcs, then it would be the sum of length of those arcs. So we do say is length of contour is sum of length of smooth arcs. Let us come to one basic result, Jordan curve theorem. A simple closed curve or a contour divides the whole plane into two domains, of which the only common points are the points which are on the curve C, and that is called the boundary points. You see, suppose this is a simple Jordan curve. You see, we are not crossing it at any point on this one, that the curve is not crossing itself at any point. This is closed one. So this is a Jordan curve. From here, if we see this whole space or whole plane is being divided into two parts. One part is this inside this closed curve, that we call interior domain, and the other is outside this curve, that is called the exterior domain. From here we do see is that for these two domains, these two sets or these two sets of plane, we do have the common points are only the points which are on the curve. They are called the boundary points of interior as well as of the exterior. In this, what it is being very clear, that is all these points whatever, they are being bounded by this curve, and the points which are in the exterior one, they could be anywhere. So we do give one basic result, that is called Jordan curve theorem. For a simple closed curve, the interior is bounded and exterior is unbounded. The proof of this theorem is a little bit involved, which requires a higher mathematics understanding. So we are not going to do this proof mathematically, but geometrically we could understand that what we mean by bounded and unbounded, interior and exterior. Now let us move to this contour integration, or come to the integral of complex function of complex variable. We will define along the path, and that we would call complex line integral. So let us define complex line integral. Let us say we do have a curve from A to B, along which a function fz, that is z is a complex variable, fz, that is a complex function on the complex variable, is defined on this line or on this curve. We want the integral along this one. How do we proceed? We will proceed in a simple manner that is similar to that real integral, that is what we have done in the calculus. What we do is, let us partition this smooth arc or this curve in n parts. That is what we are saying is, let us take z1, z2, z3 and so on, zm minus 1, zm and so on till zn, say b, n points on this one. In what manner I have to take these points? These points, because we are saying is that any arc or any curve, simple one, we are defining with the parametric presentation, that is we say z is equal to zt. So, these points which we are finding it out, Z1, Z2 and so on. So, A is equal to Z0 we are saying. We take in this manner such that I do have whatever the parameterization T I am having, Z0 we say is Z of T0, Z1 we would say Z of T1 and so on, Z of M we would say Z of Tm, and this T0, T1, T2, Tm, Tn, they must be in order, that is T0 must be smaller than T1, T1 must be smaller than T2. In this manner this partition has to be done. So, what we are doing is now we are taking this complex domain, my function my curve is from A to B, A and B are complex variables or complex numbers, and all these points we are taking in the complex one. How we are saying is that this arc we are defining by the equation Z is equal to ZT, that says with the partition we do take in the increasing order of the parameterization parameter T. In this, let us say now if I do take a point between say Z0 and Z1, Z1 and Z2, say like this one. So, here I had just noted here that between Zm minus 1 and Zm, let us say take any arbitrary point Zm star. So, between A and Z1 I will take one arbitrary point Z1, between Z1 and Z2 let us take any arbitrary point Z2, like that, and let us denote the difference between Zm and Zm minus 1. These 2 points, the distance between these 2 points, let us denote it by delta Zm. We do know the distance between these 2 points would be given by this straight line. Then if I just go with the real analysis, that is in the calculus how we have defined the integral, we say is that we multiply this value of the function at this point with the distance between the 2 points and then we add it up. So, let us define this sum Sn. N I have taken because I am taking this partition of n values as summation m is running from 1 to n, f of Zm star multiplied with delta Zm. Let us define this sum. Now, this sum is depending upon 2 things. One is where I have taken this point Zm star, and another is that is what is this partition, because accordingly I would change this distance between Zm minus 1 and Zm, that would be changing. So, as this n is changing or this partition P is changing, this my sum Sn will also change. Now, make a sequence of this Sn. In what manner? We try to take the partitions according to this n, that is why I had used here n, according to this n in such a manner such that the distance between these 2 points, that is we are defining these points say Z1 and Z2 as Z of T1 and Z of T2. So, let us take this partition in such a manner that if n increases, that is if I take the number of partition points more, then the distance between Tm and Tm minus 1, that is the distance of the parameter T at this point and this point, that approaches to 0. If that is approaching to 0, what it says is that my delta Zm, that would also approach to 0. Why? What we are saying is T is actually T will move on this line. So, if Tm minus 1 would be this arc length and delta Zm is this one. So, if this is approaching to 0, this can never be more than this arc length. So, that would certainly has to approach to 0. So, let us take the partitions in such a manner that if n is increasing, delta Zm approaches to 0. In this manner, I would get a sequence of sums Sn. Now, let us define the complex line integral in the similar manner as we have defined the line integral on the real ones. We say the limit of the sequence Sn, that we would call the complex line integral. So, limit of the sequence of Sn is called the line integral, and it will be denoted by either integral c f z dz or by this notation where this circle is in between c f z dz. This notation we are using when we do have any arc or any smooth curve. This notation we are using when we do have closed smooth curve. This is a further notations, not necessarily that we do use it, but when this notation is being used, it simply says it is on the closed curve. So we are talking about the smooth curves and we are defining this integral of complex function of complex variable. So thus now this integral would be existing, that says this integral would be defined if the limit of this sequence is coming up or is existing. This limit would exist if I just take this parameterization. Parameterization is along this line, that is along this line I can treat it as a real one. In the real one, if this function is such that this is existing, then we would say this sequence limit of the sequence is existing, we would say that our complex line integral is existing. So now this is the definition, the existence part we will see later on if we could see. Let us come, definition we have done, how to really find out this integral, that is what is the method to evaluate this integral. So let us find out what is the method to evaluate this contour integral. Let the contour C be given by this z is equal to zt. Now since this is a complex variable, so let us say I am writing it as xt plus iyt for t between the interval a to b, and the function fz is as u plus iv, as usual we used to define. Now the function of z is itself depending on the two variables x and y, that says is that f which is depending on z, that I could say is u which is depending on z rather than z. Now I will take the two real parts, that is u is depending on x and y and v is depending on x and y. So you see this is a complex function on the complex variable. We are again trying to break it into two parts where we are taking both the parts as the real one. So this is a real function of two variable, this is also a real function of two variable, and they have been joined with this square root of -1, thus we are getting is this complex one, while as this x and y are nothing but the real and imaginary part of the z. So f of z of t, now I could write as now if I write this z as a function of t, so certainly z is function of t, then x is function of t, y is function of t. So certainly I would get different parameterization, u as x of t, y as of t, and v as x of t and y of t. Moreover, we are talking about the contour C. Contour means is that my C is a differentiable arc and it has derivative is not 0 in the whole range, that says is z dash t would be x dash t plus iy dash t. So the contour integral then we are defining as integral from a to b f of z of t times z dash t dt. Why? What I am doing is changing the variable, that is instead of integrating in the z, we try to integrate it on t. So z is a function of t, so z of t, if I am taking z of t, then dz I have to write in the terms of dt. What will be dz would be, actually if z is zt, then dz would be z dash t dt. So that is just by the change of variable, as usual we used to do in the real integrals. In the similar manner we have done here, because why we could apply it more, we could see is that is we have break actually my z also into the two real integrals, and in this your u and this f also in the two real integrals. So we could do it. So that is what we are getting. Let us see that is whether we could do it or not. So, what we have defined now, our contour integral on contour C of a function f z with respect to z, we are defining as integral from a to b f of z of t z dash t dt, where z t is actually the equation of this contour C in the parameter t. Now, that says it is the integral along this contour. So, this a and b and this z t, that is actually defining, that is what is the contour. Let us see the proof of this one. Since z t is x t plus I y t, so this says is z dash t would be x dash t plus I y dash t. So, C f z d z we could write, which we are saying is that in this manner, what it would be, f z t we could write u of x y plus I v of x y into z dash t is, that is x dash t plus I y dash t, it should be y dash t dt. Now, if I multiply these two, I get from here u x dash and I times I will multiply minus v y dash. So, we do get minus v y dash, and then the part which is containing I would get v and x dash plus u and y dash. So, we do get plus I times v x dash plus u y dash. Now, since my u, v, x and y all are real, so we could treat it as a real integrals, and using the properties of definite integrals we could just break it into two integrals. Now, since all these are real ones, you see is that is what we could write. U is a function of x and y and x is a function of t. So, what we could write, u x dash dt, that we could simply write as u dx. So, you see we could write it as u dx minus v dy. Similarly, this one I could write I times integral a to b v dx plus u dy. So, what we are having is, if I see is that is, again I could write it as double integral, two integrals, integral a to b u dx minus integral a to b v dy plus I times integral a to b v dx plus I times integral a to b u dy. What we are doing is actually this a and b, they are defining, they are being defined, these limits are being defined according to the parameterization whatever we have taken. According to that, since all these, if the functions are continuous, then they are integrable. So, we do get is that all these are integrals would be existing. So, we do find it out. This method of evaluation of the contour integral will give me the integral which is required, and that would be again a complex number. This satisfies certain basic properties. As in the first one we had seen, that is those basic property, it is also satisfying those properties. First is linearity, which says is that if k1 and k2 are any two real numbers, here I am taking this k1 and k2 as real numbers, and f1 and f2 are any two complex functions defined on complex variable, then the contour integral k1 f1z plus k2 f2z can be given as k1 times the contour integral of f1z plus k2 times the contour integral of f2z. We can show it very easily using the definition. If I just go by this definition of the contour integral, we say is that with certain parameter z t, which says is that z is z t for t belonging ranging between a and b, we could write it as k1 f1 z t plus k2 f2 z t z dash t dt. Now, once we have come it up, now we see is that is all these things we could use by the definition, we can make it the two integrals, and then we would be getting is k1 a to b f1 z t z dash t dt plus k2 a to b integral f2 z t z dash t dt. This is nothing but the contour integral of f1 z, and this is nothing but the contour integral of f2 z. So, thus the linearity is being kept, that which says that contour integral is a linear operator. Now, the other property, sense reversal. In the definite integral on the real line, you have done it, that is, if we change the limits from lower to the upper, we do get that the integral is negative. This property we had seen in the complex integral of complex function on the real domain also. Here also it is being done. That is what it says is, here what we mean by the sense reversal, there we do have is that because A is less than B kind of thing. Here what we do have, if the orientation is changing, that is, if rather than having the contour C, if I do have contour minus C, that is, if the orientation has been changed, then it would be minus of contour integral on the contour C of fz dz. Again we can just prove it using our definition. We want contour integral on the contour minus C fz dz, that means the orientation has been changed. That is, if z is equal to zt is the equation of the contour C, what we do get is that t is increasing from A to B. What we do take is that if I take instead of t as minus t, we could define this my curve minus C. So, we just take z of minus t. So, that is t that minus C, that is the contour orientation is being changed, that says is instead of t, if I take the minus t on the same one. So, if I am taking is minus t, then certainly if t is moving from A to B, we do have minus t would be moving from minus B to minus A. So, it is minus B to minus A f of z of minus t, and the derivative of z of minus t with respect to t, that would be minus z dash at minus t and dt. Now, use the change the variable from minus t to plus t, that is, take the minus t is equal to some say v, and then again do so. I am doing is simply keeping it minus t is equal to t. What it would be, if minus t is say v, then as t is reaching to the minus b, I would take as minus t would be b, as t would be reaching to the minus a, minus t would be reaching to the a. So, integral b to a this limits f of z of t, z dash at minus t, so that is minus t is t. Since I have changed the variable from minus t to v, so what we do get minus dt would be dvr, that is we are writing here dt. So, we get integral b to a f z t z dash t dt. Now, here what we have, just only thing is that is the order of the limit has been changed. So, using the simple property of definite integral, we could say it is minus a to b f of z of t z dash t dt, because t is now we are teaching as a real one. So, this is a to b. So, we have got that this property is being, this is nothing but the contour integral of with contour C. Then third property, partitioning of path. Say I want this integral f z dz is on the contour C. This can be written as the sum of two contour integrals on the different contours C1 and C2, where the C1 and C2 are nothing but the partition of the contour C. Let us see here. Suppose this is my contour C, and suppose at this point D, this contour is being partitioned into two parts, that is from A to D this is the contour C1, and from D to B this is contour C2. Then we could get this integral, that is as the integral from A to D, or rather you could say is on the contour C1 and then on contour C2. Now, here it has actually this, in this example what this contour I have taken, it is not looking very impressive, that is why I should divide it in between, while I could go ahead directly in this one, because this is the same contour. You could see if I do have the contours as in the close contours I was having is a square or a triangle, you do find it out that is suppose it is a rectangle one. So, I do have in this line, and then I do go in as upwards, and then I do go over this one. So, while I could be easy, it would be very difficult to find out a z is equal to zt parametric equation for that contour, even if it is a simple line in this direction and in this direction and in this direction. Rather, if I break it into the parts, that is I just go with this integral on this direction first, and then on this direction, and then on this direction, and then on this path, it would be better, it would be much easier one. So, we do get there this property helps very much helpful, that is I could integrate on the different contours which has been added up, and I could get the sum of those integral values as the sum as the integral on that same contour. Now, as I have done this linearity with real constant, now let us take this. If I do have a complex constant as a multiple, this property we have done with the real domain actually, z naught f z d z. As we have done in the real domain, in the similar manner, actually it would be same as z naught times contour integral on the contour C f z d z. That is, whatever be this contour, this z naught, if it is a constant, complex constant, then we can always take it outside the integral sign. Then the proof is very easy. You can again go ahead with this z is equal to zt and the definition, and you could find it out that it would be easy. But from this property what we have got is, if I add up this property with our first property of the linearity, that says is that there those constants k1 and k2, now we can change to the complex constant as well. Even then our property of the linearity would hold. So, we come to the basic property about the absolute value of the integral. That is, what will be the absolute value of the contour integral f z d z on the contour C. We have defined by definition, this is nothing but the integral a to b f z t z dash t dt, and then t is actually the real variable. So, we could use the similar property of the real variable, and from there we could get that this should be less than or equal to integral of a to b f z t z dash t dt. Now, from using this one, this f z t into z dash t, its modulus value, absolute value, we do know that absolute value of the product of two complex numbers would be nothing but the product of absolute values. So, we could write it as absolute value of f z t into absolute value of z dash t. Now, if this f z t, that is, it is absolute value of f z, if I could find it out at upper bound of this f z on the contour C, let us say that upper bound is capital M, then that would be a constant. This M may be complex one as well, or the real one, since it it is a f z absolute value of f z, so it has to be real constant. So, this real constant I can take it out, and then what it would be the less than or equal to m times integral a to b absolute value of z dash t dt. So, this integral a to b z dash t dt, this, if we do remember, this is nothing but the length of arc. So, we could say this is ml. So, what we do have got, that is absolute value of this contour integral is less than or equal to the m into L, where m is nothing but the maximum or that upper bound of the function, absolute value of the function f z on the contour. Let us do one example. Integrate the function f z is equal to z square from 2 to 2 plus I. Now, let us this example which we would be doing is, we would be actually trying to find it out, as we have seen, that is from a point A to B on the complex plane, we can reach in all infinite many ways. So, we will try to reach to, that is, we will try to find out this integral along different contours, so that is different paths, and then we will try to see, is this path or this contour is really making a difference in the evaluation of integral, or it is not making. So, let us take this first example, where I am taking is that function f z is z square, and the points, 2 points we are taking is 0 and 2 plus I. So, let us take the figure, this one, we do have this point 0, this is 0 0 in the complex plane, the point 2 plus I, that is, this is we would say is the complex plane, we can always define as the 2 dimensional plane, where this one dimension we say is this is the x dimension and this is the y. So, z is x plus y, that is any point on this one x plus iy we are defining as x comma y. So, 2 plus I means is that is 2 and the multiple of I is 1, that is 2 1. So, I have to reach from this point to this point. Now, I can reach to this point in many manners. Either I can reach first from 0 to 2 and then 2 to 1, that is along this contour C1 and then contour C2, or we can directly reach along this straight line from 0 to 2 comma 1, that is this contour C3, or I could treat a different parameterization, that is here what I have, when I have said is that C1 plus C2, I mean is that is I will take one contour C1 and another contour C2, or I can take this complete line, that is from 0 to this 2 plus I in this path as single contour, and that C4 that I would be saying. You see is that parameterization, as I said is that is why this property of partitioning of path is important, that is we do have is the parameterization would be a one. This here is the first simple example I have taken, in which I could say is that from here to here I could either use single parameterization for whole contour, or I can have one contour, one parameterization for this, another parameterization for this. So, let us start one by one. So, first I am taking integral along this path, and this path I am breaking into two paths, one is C1 and another is C2. So, C1, if I see here I am having is I am moving along the x axis, that is along the single line this one, and y is being kept as a constant. So, and that constant y is actually 0 because it is on the x axis. So, if I take x is equal to t, the parameterization, so I do get that y is 0. So, I would be getting this x plus I y, that is x t plus I y t, x t I am taking it as t. So, t plus 0, that is t only, and my t is varying from 0 to 2, and C2, now I am taking the different parameterization. The C2 if I do take, if I treat simple this xy plane, the C2 is the line which says is that your x is equal to 2 and y is varying from 0 to 1. So, I will take the parameterization for y, that is y is equal to t, where t is varying from 0 to 1 and x is constant 2. So, I could use this parameterization zt as 2 plus it for t between 0 and 1. So, you see here what I have done is I have taken one contour C1 for which I have taken one parameter, that parameter is actually x, and in this I have taken another parameterization. In this one actually my parameter t is y. So, these paths we had find it out. Now, I will go the contour integral along the path C1 and along the path C2. So, first C1, for the C1 z dash t would be, because z t is t, so z dash t would be 1 for the range between 0 to 2, and for C2 z dash t would be, this is constant, so it would be I only in the range 0 to 1. So, now using this property of the partitioning of path, integral along this contour C f z d z, I could write contour integral along the contour C1 of f z d z and C2 along the C2 f z is z square. So, let us evaluate first this C1 integral. C1 f z d z I could write, now C1 we see the parameterization is from 0 to 2. So, my a and b are 0 to 2. So, if I take this by definition it should be f integral a to b f z t z dash t dt. I would have 0 to t f z t, z is z square. So, I would get is from here z of t is t. So, z square would be t square and my z dash t is 1. So, I would get simply dt. Its integral is simply 8 by 3 because t cube by 3 evaluated from 0 to 2 it is giving me 8 by 3. Now come to the second contour. Second one is my contour C2 is 2 plus it for 0 to 1 and z dash t was I. So again using the definition, integral along the contour C2 fz dz would be integral a to b fz t z dash t dt. Now substitute it. So my fz is z square. So here if f of z of t, if I do write, I have to write 2 plus it whole square. So 2 plus it whole square, z dash t is I, that dt. So this whole square would be 4 plus I square t square, that is 4 minus t square plus 4 it multiplied with I, we would get it integral 0 to 1 4 I minus it square minus 40, because plus 4 it into I, that would give me I square is minus 4, so minus 40 now dt. So integrated with respect to t, here I would get 4I into t evaluated from 0 to 1, that would give me simply 4I minus I t square integral from 0 to 1, that would give me t cube by 3 evaluated from 0 to 1, that is I by 3, and then minus 4t, its integral would be 2t square evaluated from 0 to 1 will give me only 2. So what we would be getting is 11 by 3I minus 2. First integral we have got as 8 by 3. So now the whole integral, that is along this path from point 0 to 2 plus I along this path C1 and C2, what we do have, we do add up both the integral, that is integral along this contour C1 and the integral along this contour C2. So along the contour C1 we have got 2 plus 2 by 3 plus 11 by 3 I, because there we were getting is 8 by 3. So 8 by 3 minus 2 would be giving me 2 by 3 plus 11 by 3 I. Now let us come to the second part, C3. C3 means that is the straight line from 0 to 2 plus I. What will be the equation of this arc? This arc we are having is, that is, this is straight line with the orientation as 1 by 2. So what we would be getting this line, if you do see y is equal to 2x from 0 to 2. So let us again put my parameter as y as t, then sorry, x as t, let us say y is equal to half x, actually, yeah, what we would be getting is y is equal to 1 by 2x. So 2y is equal to x. So let us take y as t. So y is ranging from 0 to 1 and then x would be 2t. So now I am getting is x is 2t and y is t. So I am getting is that t as 2t plus it and t we have taken as y. So t is ranging from 0 to 1. So this is the parameterization of this straight line from 0 to 2 plus I, this one. So what we do get is, that is along this path, if I find out what is its derivative, it would be z dash t would be 2 plus I. Now evaluate the integral along this path C3, that is contour C3 fz dz. We just go with the definition a to b fz t z dash t dt. Now a and b are here 0 and 1, fz is z square. So when I write zt is my 2t plus it. So we could write it as 2 plus I times t actually. So that whole square, and z dash t is also 2 plus I. So we are getting is 2 plus I t whole square into 2 plus I dt. Now this 2 plus I, this is a complex constant, this is also complex constant. So what actually we are getting is 2 plus I whole cube into t square dt. Now t plus I cube, I whole cube, that is a complex constant, and we do know with the property that if it is a complex constant, that we can take outside the integral sign. So then the integral left would be only t square with respect to t on the interval interval 0 to 1. So what I would get is this one, 2 plus I cube 0 to 1 t square dt. This integral is nothing but 1 by 3, because t cube by 3 evaluated from 0 to 1 will give me only 1 by 3. So I would get 2 plus I whole cube. 2 plus I whole cube is what? 8 to cube 8, I cube would be minus I plus 2 into 3, that is 6I times 2 plus I. Again you simplify it, finally you will get it is 2 by 3 plus 11 by 3I. You can evaluate by yourself, it is very simple calculation. So we have got, when I have gone with this path, I have got 2 by 3 plus 11 by 3I. When I have got directly along this path, again I have got 2 by 3 plus 11 by 3I. Now with the same path, if I use the different parameterization, that is what we have called C4. So let us see, that is how we can have the different parameterization once more. We want along this path different parameterization C4. That is with the same parameter t. Let us see, you see is that is here I am not going to explain, that is how we have find it out. Let us see first this parameterization. Zt is t from 0 to 2 and then 2 plus I t minus 2 for 2 to 3. You see this part is easy because along this path it is just the x1. So we do have is it is simply t, x is equal to t and y is 0. Along this path when we are going, I just want the parameterization in the same continuation. That is, in the first one when I have breaked it into C1 and C2, I have taken this a different contour and the different parameterization. But now here what I want the whole thing as the same contour. That means I want same equation. In the same equation if you see, you can check, that is here what we are getting is, that is we are getting is that x is being fixed as 2. So that is all right. Now for this y is ranging from 0 to 1, but if I do take is 2 plus y, then y I am not having this parameterization. Parameterization we do had is for in the first part as x is equal to t. So let us say is, that is rather than taking is x and y, let us try a different kind of parameterization, just the thinking about it. It is not that is in the simple manner we are finding it out. So we have got it is t, and from here to here I require, so I have got, that is it has to be this x part has to be constant and y part has to vary. So the t has to come in the y part, and this part we want from 0 to 1. So I have used it t minus 2, so that now this onwards, that is I am taking a contour which is smooth join end to end. That means my t has to move along, that is my t has to be more than 2. Remember it, that is what we are, how this parameterization we are finding it out. This t I cannot go back as 0 to 1, in that I have to have the different contour. So what we are having is, that is this one we are moving from here, and we are saying is that it has to move from 2 to 3. The partition, if you do remember what I said is that we take t1 is less than t2 and so on. So this is 2 to 3, so for that, because I require here only 0 to 1, so we have taken t minus 2, so it is 2 to 3. I cannot move any other ahead also because this has to be same. So you could say this is, as such it is looking very simple one, but I do find it out that if I am making it a different contours, and for the different contours if I am taking different parameterization, it is not making any difference, since we have already proved that is in the length of arc that different parameterization does not change the length of arc. Now here is, that is the integral of arc. So here when I have taken this one, then z dash t would be 1 in the range 0 to 2, and it would be I in the range 2 to 3. So now find out the contour integral along this contour C4. Fz dz, by definition it has to be a to b fz t z dash t. Now this we have to write in the two parts. One is t is ranging from 0 to 2, and then t is ranging from 2 to 3, the function is changing. So here z is, square would be coming to t square, and in the second case the 2 to 3 z square would be coming as 2 plus I times t minus 2 whole square, and z dash t is in the first range 0 to 2 is 1, and the second range 2 to 3 is I. So we do get 0 to 2 t square dt plus 2 to 3 2 plus I times t minus 2 whole square I dt. So this first integral is easy, that is it is t square evaluated, so integral would be t cube by 3 evaluated from 0 to 2, it will give me 8 by 3. The second one, now change this variable t minus 2 to let us say t again, So, we would get the ranges from, if t is from 2 to 3, then t minus 2 would be from 0 to 1. So, it would be 2 plus I t whole square, that is again multiplied with I, we get 4I minus I t square minus 4 t dt integrated from 0 to 1. I would get it as 4 minus I by 2, I by 3 t square by 3. So, it should be minus I by 3 minus 4t well, integral would be 2t square evaluated from 0 to 1 would be minus 2. So, what we would be getting is 8 by 3 plus 11 by 3 I minus 2. Again we are getting it is 2 by 3 plus 11 by 3 I. Now, what we have got, if I have taken this way the path or I have taken this way the path, both times the integral of the function is coming the same. That is the, in which path we are moving, that is not making any difference. You can say that is I have used only the straight lines, and for this this first path, that is C1 plus C2, I have used another parameterization also. Even then we have got it is going ahead and we are finding it out that it is the same integral. You can choose some other path also, you can use a part of parabola or part of circle, something, anything like that kind of thing you can also choose and think of the parameterization, and then you can calculate this integral. In this function you will find it out that all the time you would get this integral is same. Now, what it says is that if this integral is same, which is not depending on the path, that is on which path, on which contour we are evaluating, it says is that if this kind of thing is happening, of course we are not knowing is that is when it will happen, or we are not having here any condition that is under what for what functions fz this will happen or what contours it will happen. Actually contour is not mattering, so it says is that the property of function, it has to be some important thing that is which would tell us that is on which functions this can happen. So, before reaching to those properties, let us just find it out that if this is happening, that is if for some function we are finding it out that integral along the different contours is coming as the same. In that case we can use another formula or another method to evaluate this integral, and that method we are getting is simply directly integrating the function from z1 to z2, where the z1 is the point from where this contour is starting, that is t is equal to a, and the z2 is the point where the contour is ending, that t is equal to b. So, if you remember that is differentiation of complex functions. So, if you just take this antiderivative formula which we had used in the real domain as well also. So, we will use the similar kind of result here we can use. So, let us say in this example itself, z1 to z2 fz dz we could say 0 to 2 plus I z square dz. Now, z square we are taking as variable itself, integrating with respect to z. So, we do get is z cube by 3 evaluated from 0 to 2 plus I, which is nothing but 2 plus I whole cube by 3, that you have to see is that this is how we have got in the second one, that is in C3. So, it is 2 by 3 plus 11 by 3 I. In that case it is free of the path of integration. Let us take one more example. Integrate from minus 1 to plus 1 the integral z bar, that is complex conjugate of z, that is x minus iy. Let us take this path, we have minus 1 to plus 1. So, let us take one path from minus 1 to plus 1 in this orientation, that is this upper half circle, and another path here taking is lower half circle in this orientation. So, let us start. So, this two paths C1 and C2. For C1, this is in this orientation. If you do remember, we have done one example where we have introduced the circle, and we said is that it should be actually there the circle was moving anti-clockwise. So, it would be actually minus of C1, that would be my circle anti-clockwise. So, it could be denoted, the parameterization would be e to the power it for 0 to pi, because what if you do just get is the polar coordinates kind of thing is, that is your x is this one and it this t is the angle between this one. So, t is ranging from 0 to pi. then using the property of that contour minus C1, we could say minus of contour C1 like that one. So z dash t along this would be I times e to the power I t. So if I just evaluate this integral around the contour C1 f z dz, what we would be getting is integral a to b f z t z dash t dt is, using that property of sense reversal, it should be minus integral 0 to pi e to the power minus I t. Function is z bar. Z bar means is its complex conjugate. So if the function is e to the power I t, then its complex conjugate would be e to the power minus I t, I e to the power I t dt. So what we have got, it is just I. From here this e to the power minus I t into e to the power I t is 1. So minus I integral 0 to pi I, that is we would be getting minus pi I. Now let us take the another path. This path if I do take, this is moving anti-clockwise. So this C2, my parameterization would be zt is e to the power I t, where this t is moving from pi to 2 pi. Again my z dash t would be I times e to the power I t. So along this contour C2, f z dz would be f z z dash t, that is pi to 2 pi e to the power minus I t, I e to the power I t dt, because my function is z bar. So it is e to the power minus I t. Again what we are getting is I integral of I dt, I is a constant that we could take it out, 2 pi minus pi, that is pi. So what we are getting is pi I. Now we see, if I have taken this function complex conjugate of the value z itself, then along these two paths, which paths we have taken on this circle, we have got that our integrals are not same. You can take actually this line minus 1 to plus 1, you can take along this x axis also, that is another path you can take and find out what is the integral. So here we have got one example, one function in which this path is mattering, that is according to the path the value of the integral is changing. The properties which says is that this is happening, that we will see later on. Let us do one more, that is the absolute value of the integral. That property also I just want to have one example, that is estimation of integral. So find the upper bound for the absolute value of the integral of z square from 0 to 1 plus I on the straight line. Let us take, this is a straight line 0 to 1 plus I. On this I want the integral z square and its absolute value. So what I will take this contour is straight line 0 to 1 plus I. So this would be t plus I t, because this line is x plus x y is equal to x. So I would have t plus I t for t ranging between 0 and 1. Z dash t would be 1 plus I. Now if you do remember, that property says is that absolute value is less than m times L, where L is the length of arc and m is the value highest value, which is the upper bound of absolute value of fz. So first the length of arc. Length of arc, either I can get it, that is the length of arc, this is the length of this straight line, because it is 0 1 and this is 1, so it should be square root 2 directly, or we can calculate using this formula, z dash t is 1 plus I, absolute value of this one, absolute value of 1 plus I is square root 2, evaluated integral 0 to 1, we do get it simply square root 2. And fz is z square, absolute value of z square along this line, if you see z is going to be along this line, the maximum value could be less than 2. So what we do get is that the absolute value, if I do use that inequality, ML inequality, we do get 2 root 2. What is the actual value of this integral? We just know is that this integral we evaluate if fz t z dash t form, I would get it 1 plus I cube time 1 plus I cube into t square dt, that is 1 plus I cube by 3, which is minus 2 by 3 plus 2 by 3 I. Its absolute value is nothing but 2 root 2 by 3, which is already smaller than 2 root 2. So this is we have established. So today we had learned actually the integral of a complex function on the complex variable along some path, that is we call contour integrals. That is all for today. Thank you.